The Hubble tension is the growing discrepancy between measurements of Hubble's constant. This is the constant that tells us how fast the universe is expanding right now. Our best model of the universe as a whole, the cosmological constant, lambda cold dark matter, or LCDM, says that it is a constant everywhere in the universe. We have two ways of measuring Hubble's constant, and if the LCDM were correct, and our measurements were correct, then the two methods should agree with one another within the bounds of error. They don't, by a lot. The tension between the two is so extreme that it is at the point of being 6 sigma, or 1 in 285,715, likelihood that we would randomly see a discrepancy like that, given the bounds of error on the two measurement methods. The CMB measurements are based on observations of the cosmic microwave background, CMB. This is the oldest light we can see, the microwaves that emerged when the universe first became transparent to light about 380,000 years after the Big Bang. By measuring temperature and polarization fluctuations in the CMB, we can determine what Hubble's constant is compatible with the CMB. It turns out to be about 67.66 plus or minus. The local distance ladder is more straightforward. You just measure the distances to objects further and further away, and measure how fast they are moving away from us, and you get a measurement for Hubble's constant. That measurement is at around 73.04. At a 2015 survey of conference attendees called Beyond LCDM, 69% of participants believed that new physics was required to solve the Hubble tension. Now, this clearly wasn't a very scientific survey, since people attending a conference called Beyond LCDM would likely be interested in theories that include new physics, and not say that the tension is caused by something we don't understand about how to measure things. Not understanding how to measure things correctly is often called systematic error, because such measurement errors tend to all agree with one another, instead of random errors which tend to disagree. This is why it has become very important to try to measure both methods in many different ways that are independent of one another. That is why the recent publication of measurement results using data from the James Webb and Hubble space telescopes called Tip of the Red Giant Branch, TRGB, is so important. It provides a completely independent way of measuring the distance ladder, and it agrees with other distance ladder measurements. One of the biggest problems in astronomy is that space is really, really big. While the distances to closer stars can be measured using stellar parallax, by measuring how they move against the background of more distant stars as the Earth moves in its orbit, for anything further away than 1,000 parsecs we need to use other methods. Over the last 100 years, astronomers have developed a variety of tools and methods for measuring distances. These are collectively called the cosmic distance ladder. When it comes to trying to measure distances to other galaxies, astronomers can rely on things that have a known, reliable brightness. For stars and galaxies further away, up to about 40 megaparsecs, or about 100 million light-years, they use Cepheid variables. These are stars that vary their brightness over time. The brighter they are, the longer it takes for them to vary their brightness. This lets us know how far away they are. Edwin Hubble first used Cepheid variable stars to measure the size and expansion rate of the universe in 1929, although he got the scale wrong. As you get beyond 100 million light-years, we need something much brighter, so we use Type 1a supernovae, which are also a standard candle of brightness. They can also use other brightness measurements, including the tip of the red giant branch method. The idea is to use the brightness of the brightest red giant stars in a galaxy as a measure of distance. The brightness of red giants maxes out at a predictable magnitude because of how stars evolve. Take our Sun as an example. Our Sun is on the main sequence because it is burning hydrogen for fuel at its core. In its outer layers, no fusion takes place. When the hydrogen runs out at the core, the hydrogen in a shell around the core will continue to fuse. Hydrogen fusion produces helium, which will accumulate there like ashes from a fire. This causes the star's temperature brightness level to migrate to the upper right of the diagram, cooling down and brightening as the star expands. Our Sun will one day expand beyond the orbit of Earth, swallowing the inner 3 planets, including our home. the sun will burn away all the water on our planet, oceans and all, about 2 billion years from now. All the carbon dioxide will outgas, turning the Earth into a hellscape like Venus. Humans will likely be unable to survive when the Earth becomes a moist greenhouse planet with surface temperatures too hot for the human body. In any case, back to the sun. All that accumulated helium ash increases the density at the star's core, which causes it to contract. The core contracts so much that it enters a quantum state called degenerate matter, which stops the contraction. As the helium continues to accumulate, it causes an increase in pressure and temperature to the point where it can start nuclear fusion into carbon. At that point, our sun will experience a relatively brief process called helium flash, where fusion starts at the core and spreads into a runaway reaction. This reaction briefly increases the energy production of the sun to about 100 billion times its normal output. For a brief moment, the sun will produce as much energy at its core as all the stars in the galaxy output. This runaway reaction explodes the core, fusing massive amounts of helium into carbon until normal thermal pressure takes over. You can't actually see the flash, however, because all the energy is used up in expanding the core. After that flash, the star will migrate from the tip of the red giant branch to a new state on the diagram with higher temperature and lower brightness. It then shrinks over about 10,000 years and becomes an orange-yellow subgiant, perhaps 40 times its current diameter. Arcturus is such a star. This discontinuity in the evolution of red giant stars is predictable enough that we can use it to measure how far away they are, even in other galaxies. The recent paper uses this method to calibrate another distance measurement method called surface brightness fluctuations, SBF. SBF is a measure of the fluctuation in the brightness of a galaxy across its surface. Since galaxies have many billions of stars, which are all discrete points of light, as one scans across the surface of the galaxy, the brightness fluctuates. This fluctuation is smaller the further away a galaxy is, because many more stars are present in any given pixel of the measurement camera. This means that the galaxy has a more uniform brightness as far as we can measure. In the study, the TRGB measurements were made between 15-20 megaparsecs, while the SBF distances went out as far as 300 megaparsecs. This is a really common technique where astronomers use an independent method that works over shorter distances to calibrate another method that works over longer, sort of like using a banana for scale. The TRGB tells us how to measure SBF distances. The paper solves an important problem in that it completely avoids Cepheid variable stars and Type 1a supernovae, which are common calibration methods. If we are all using the same ruler to calibrate our tape measures after all, and the ruler is wrong, then we can't trust the tape measures. This rules that problem out, because it agrees with measurements that do use Cepheids and Type 1, a supernovae, such as the SH0ES collaboration. We can also have greater confidence in those results. In other words, we have completely independent confirmation that the distance ladder method is correct. The CMB method, on the other hand, doesn't rely on measures of distance at all. It relies on fitting a model to the cosmic microwave background and determining what Hubble constant would best agree with it. CMB measurements come from a succession of satellites. The first was COBE, which was relatively inaccurate. The second, WMAP, produced a great deal of data, which was far more accurate. The most recent is Planck, which is the most accurate of all. Other methods are also in the works, such as megamasers, which blast out of black holes, gravitational waves from colliding neutron stars, and fast radio bursts, which may come from magnetars, neutron stars with a powerful magnetic field. So far, none of these methods is particularly accurate. Suppose that all these late universe measurements, however, agree with one another and disagree with the CMB measurements. There are at least 100 different explanations. The simplest is to say that Hubble's constant has changed over time, and that LCDM is at best a first-order approximation of a more complex universe. This would not be too surprising, since there is other evidence that the LCDM and its underlying model of the universe cannot explain the large-scale structures in the universe. The reason we believe that Hubble's constant is constant at all after all is because it is a constant of integration when we solve the Friedmann-Lemaitre-Robertson-Walker or FLRW equations. If the assumptions that we put into the Einstein equations that produce the FLRW are wrong, then the result will be wrong. One of those assumptions is that the universe is isotropic. If the universe is not isotropic and has a very large-scale structure, it could easily have a changing Hubble's parameter. Other ideas are that dark energy is not constant, which is not a feature of FLRW but is the lambda in LCDM. More extreme ideas propose new kinds of particles, fancy interactions with dark matter, and modified gravity. Some of these proposed ideas have a lot of problems. The main categories of proposed solutions are those that say that something was different about the universe early in its history, something changed later in its history, or Einstein was wrong. Early dark energy theories such as this one propose that the early universe behaved differently than we think, while we are good in the later universe. The early universe was being pushed to expand more quickly before the recombination that released the CMB than it should have, perhaps driven by some quintessence field that we call dark energy. This would push the measured Hubble constant higher, aligning better with distance ladder measurements. Late dark energy theories are just the opposite. They propose that the early universe is exactly how we expect it to be, while the later universe isn't. Rather, something strange is going on with dark energy in the last few billions of years, causing the universe to expand more than we expect. This explanation tells us that the Hubble's constant actually is different in the early and late universe. Both of these explanations have their problems. Early dark energy has to be finely tuned to start and stop at the right time, and may cause issues with large-scale structures that we observe. Meanwhile, the late dark energy can have issues with other late universe data, such as baryon acoustic oscillations and weak lensing. A thorough scientific review of these ideas can be found here. Modified gravity goes further, suggesting that Einstein's theory itself, the bedrock of all gravitational theories, is wrong, or at best an approximation. So far there is no good contender, partly because all of them need to agree with Einstein's theory in the solar system. One thing is clear, however, we are likely to see some new physics from the Hubble tension. At this point, it seems unlikely that systematic error is the culprit.